Good afternoon, everyone. So this talk is going to be slightly different, or maybe quite different from all the rest of the talks in the session so far. It's more of a maybe in the vein of position paper rather than something offering solutions. But I think it poses some interesting challenges, and the interesting, or at least something that made me quite excited, is that you guys are already thinking about these problems and making progress on these. So a caveat going into the talk is I would have said probably this talk is 3 months behind the curve because the field is changing so quickly. That's assuming that I kept up with the field 3 months ago. So we'll see. But I think the outline of the talk is I'm going to provide a brief overview of the power system and how the power grid runs, and then sort of outline some of the challenges and the drivers and challenges of moving to clouds. Okay. So essentially, a power system is generation, transmission, and distribution of power. Transmission and distribution are sort of differences in the scale rather than anything else. They're basically transmitting from one end to the other. So you have power generated at generation stations go on what's called a bulk electric system that transmits power at high energy levels. And then you come to your neighborhoods where it's distributed to consumers. So the electric grid we have, the North American grid, is considered sort of one of the engineering feats. It's top of the list in the last 100 years. It basically impacts of every other sector we can think of, and the structure of American grid it's divided into 4 interconnections, and it's more or less similar in the rest of the world as well. I mean, we focus on the U.S. grid in our research, but we do look at other grids, and sort of there are usually 2 or 3 interconnections or 4 interconnections in other big countries or regions as well. So it's pretty similar. So I think looking at this should give us an idea of how grids work everywhere else. The regulatory structure might be different. So who's in charge? At least in North America, there is an organization called North American Electric Reliability Council. So they sort of have the authority to sort of oversee the operations. They derive their authority from the Federal Energy Regulatory Commission. We probably don't need to know the hierarchy, except regulation, I think, plays a huge role in the adoption of clouds by the power sector. So that's the only reason I want to mention that it is kind of a semi-regulated industry, and sort of that's a barrier. So here are the 4 regions that I mentioned before. Western interconnection. The thing in multiple colors is the Eastern interconnection. We don't need to worry about the divisions there for now. And then Texas is its own interconnection, and Quebec is its own interconnection in Canada. So just sort of a background. So what we saw that the power infrastructure is about generation, transmission, and distribution. But more than the physical infrastructure, there's also a cyber component to this. So essentially, it's a very tightly woven cyber-physical infrastructure. The electrical infrastructure is monitored and controlled using cyber components, and that's been the case for almost half a century now. Most people say, "Oh, we're going to a smart grid," and a lot of power faculty I work with, they get sometimes offended with that term because they say we are going towards a smarter grid. We're already much smart with how we do things, and some people assume smart grid means combining power and communication infrastructure, but we already have communication infrastructure, had it for 50 years now. So at the bottom you see the sensing and the communication infrastructure, and these big computers here represent sort of the computation that goes on to keep this system running. Just to give you a sense of the scale, the 4 interconnects are different, but they have ties. DC ties, but each interconnect you can think of is a single machine, a single interconnected machine. It's like probably the equivalent is the internet, except that internet is not sole purpose is not producing and distributing electricity like it's sort of a single purpose machine. So in terms of operating this system, it's typically done through supervisory control, supervisory data acquisition. So it's called SCADA systems. And then each region of the electric grid is actually controlled and operated by multiple redundant control centers, and each of them is supported by a data center. So you have to think, I think we are moving away, we are sort of becoming a monoculture on the internet side of things, but power people still maintain diversity for reliability reasons, that if they have a system, they'll have a redundant system to back it up, and they'll use hardware from different vendors. Of course, the vendors are now all using monoculture. It's typically same operating system across all this stuff. So I think if you go at a lower level, it's still a monoculture. But the reason I'm mentioning this is to understand the emphasis these folks keep on reliability and sort of having a backup. I don't know how they tolerate limping stuff. Might be interesting to see that, but crash failures, at least they sort of plan for that. So here is examples of the kind of operations that take place in these systems and the timescales. There are real-time operations, and real-time, our internet real-time, or sort of the computing real-time, is quite different from real-time for the power folks. So the fastest probably right now is the protection system. They have to make decisions within 4 milliseconds to take actions on the system. So that's sort of the order that they have to work at. And then slowly you go up. You have frequency governors and generation control, and stuff goes from seconds to minutes. And then economic dispatch. So economic dispatch basically decides which generator should produce how much power, and it happens every 15 minutes. Now that's day-to-day operations, and I'm not covering all the systems that are used. I'm just sort of want to give you a flavor for the timescales. And then there are planning operations where they forecast the load day ahead, and there are also longer-term forecasts. And then they do unit commitment. So that's where, for markets where the power is deregulated, it's sold in the markets, so it's day-ahead markets, and there are also hourly prices. But they start off with a day-ahead prices, and then they refine them depending on the load conditions. And then maintenance and planning in the order of weeks to a month. So if you're familiar with the Enron case, Enron made money by sort of scheduling maintenance when it's convenient, when they can make money on the markets. Essentially, that's the scam. And then generation and transmission planning is up to tens of years. So these are the scales. So what is our interest in moving stuff to the cloud? Right? I'll come to it, but I just want to use this slide. So I think this millisecond and second and maybe even automatic generation control, these are feedback based. And in this paper, we're not proposing that they be moved to the clouds. I think even what we proposed, a lot of people found heresy that we're suggesting that some of these things should be moved to clouds. So what we are looking at is open loop, which is human in the loop, so state estimation, economic dispatch, forecasting, and unit commitment stuff. They're still real time. They're still within minutes to sometimes hours, and especially marginal pricing. They we believe could benefit from moving to the clouds. Okay, that's our supposition, and then we are looking at what are the benefits and challenges in doing so. So here is a reference diagram that captures sort of this. NIST created this a couple of years ago. Captures the different interactions between entities and operations that go on. So what I want to highlight, it's a soup of a diagram. I think the slides will be available, so you can look, or you can look in the NIST document. So this is the traditional operations, transmission, distribution, and overview of those things. And then here are the real networks. Here are the markets, typically run by the independent system operators. And then here are the service providers. With this move towards modernization of the smart grid, here is new business models coming in with smart meters and service providers sort of using that information. So billing and also connecting home to either the billing or the provider, so where you can control stuff directly either by the provider, or you can control it via the internet as what happens in your home. So already there is, when I say moving applications or power system applications to the cloud, not to say that it hasn't happened already. there are applications in the cloud, and this is why I want to point this out. So if you see here, there is internet and e-business. So applications that are already using internet or e-business, I think the sector is comfortable and they've already moved. So let me show you that. So meter data management systems, their job is to collect and process the meter data from smart meters and sort of bill you as a third-party service to the provider. And demand response solutions, where you're responding to price signals and changing your usage of power. There are already services on the cloud. Honeywell's Aquacom, GE's GridIQ, AutoGrid, and lots more. And IBM, Microsoft are also players in this space. So these things already moved to the cloud, and that's not an issue. And the characteristics of the applications that moved is they have already been internet-centered, and they're not critical for the power system itself. Although soon demand response might become critical, and that might be the transition for the power sector to become comfortable, in the sense that right now it's not critical, so they put it on the cloud, and then it becomes critical, and they say, hey, cloud worked fine so far for us, so yeah, maybe it's not that bad. So Mike's talk today actually set the stage very well for, I believe, for my talk, because it's all about gaining trust in the cloud. And the question is, how do we enable the power sector to gain trust in the cloud? And our impression is that, so how is the power sector different from any other sector, right? I mean, why should anything be done differently for this sector? And our view is that the barrier for the power sector is higher than for other sectors, for the simple reason that the risk is higher, not just for the sector, but for the society as a whole. So there was recently a presentation where I saw a slide where, you know, if you could say, oh, banking, if the systems are down, banking will lose so much money an hour, telecommunications will lose so much an hour, and so on. But if you lose power, all these sectors will lose simultaneously, so the impact is much, much higher. So I think that sort of sets the barrier for this trust establishment at a higher point than usual. Anyway, but there might be people with a different opinion, but that's our view. So now we already know this consumer-facing applications have moved to cloud. So why not move these other real-time, but probably not that critical? So not feedback applications or control applications. Why can't we move them to the cloud? So the question is, why should we move them to the cloud? And if you analyze these applications, you see that they have varying computational needs, either because they're used occasionally or because the computation, the amount of computation needed changes based on the system state. And it seems to us that just like other sectors are taking advantage of this cloud infrastructure, this sector could benefit quite a bit in terms of cost. The other advantage, at least in our view, is that the power operators, they're really good at understanding how their power systems run. But I don't know if they're able to attract the same kind of talent in terms of the cyber infrastructure and maintaining and running that infrastructure as probably these cloud providers could do. And this is the point that I think Mike made quite well today morning. So just to quickly go through the applications. So these are the kind of applications run, and as you can see, the kind of computation needs vary. So you could leverage the elasticity provided by the clouds. So let me move on. So here are the drivers. They're not really that different from other applications: cost saving, elasticity, and improved reliability. Today we are not able to go beyond N-1 criteria for analyzing contingencies, but if we have the power of going beyond, especially when the system is under stress. So what does N-1 criteria mean? Being able to tolerate one failure, a line failure or generator failure. But we could analyze more failures, 2 lines, 2 generators, and so on, when needed, and we could leverage the elasticity of the clouds for that. So it could improve reliability. opens up markets for data analytics and innovation. One of the other issues we see in the power grid is it's quite locked up, vendor locked up. And security, and I mentioned about dedicated talent, wider view, and so on. So what are the concerns? The security is that you don't have hard guarantees provided by the cloud folks right now, but it increases exposure, at least from the sector's view. Real-time computation, some of these things have to have, real-time doesn't mean fast, they need deterministic response times, and which is not always true. Our understanding is clouds run on best effort, right? Same thing goes with reliability. And regulation. Regulation is a huge bottleneck because right now these companies have to go meet strict compliance rules. In recent discussions, what we heard was that straightforward applying NERC if people want to move clouds is that power sectors will have to demand background checks on all the employees using at the cloud operator and maybe the tenants as well. So it's not set up for using clouds right now. So I'll quickly go through some of the issues. So confidentiality, we talked about market advantage that Enron gained. System data you could leverage for cyber attacks if you know the system specifics. Integrity of computations and data. When I run a control algorithm or an operational algorithm in the cloud, I get the results back. How do I know I can trust these results and make a control decision based on them, right? So just to sort of give you a flavor, these are not different, but I'm trying to put them in the context of the power system. Okay, so Mike talked about end-to-end, and I'm calling that as cloud as a black box. So I get cloud is what it is, and I'm trying to create an assured service by composing or doing something on my side. So for example, I could say, okay, cloud doesn't provide me any confidentiality guarantees. I'm going to put my stuff using homomorphic encryption and then do my computations on top. Not really practical today, but a thought, just to give you how it might work. The other option is to do problem transformation. You can transform a power problem linearly and then do computations and invert it. Wisconsin folks did that for optimal power flows, and we have something under review for contingency analysis. The perturbation is not reversible, but we take advantage of some additional computations we can do locally to sort of help with that. So this is a flavor of something that one could do for confidentiality, and we could do similar approaches for integrity. So multiple independent executions. It increases the cost, but at least you get you can probably have better confidence in the results if multiple executions in different clouds give you the same answer. Or you could run a high fidelity computation in the cloud and check it using a low fidelity computation locally to see if they're in range. Some ideas on how to compose assured services. And I didn't touch data storage because Mike went into quite a bit about data storage today morning. So the questions are, what properties can be achieved in this way for the power sector applications? And as you can see, there are overheads in each of these approaches, and do the costs involved outweigh the benefits of actually moving to the cloud in the first place? I think it's a big question. The other side of the solutions is cloud providers themselves might provide, so instead of end-to-end, it's like end-to-middle. They provide support for some of these security properties, improved isolation. So there is work in this space, or fault-tolerant infrastructure. So there is work from Cornell on ISIS-2. So they call it Grid Cloud, I think, trying to build fault-tolerant systems in the cloud for the power sector. Or maybe there might be in the future multi-tenant support in hardware to provide some isolation that way. So this is where the cloud providers are sort of supporting some of these properties. The question is this economical to do so, and how many people would be interested in it? And an interesting thing that Adrian pointed out, and I'm interested in looking at, is the cloudonomics. He said the private clouds are not really that economical, and right now that's what power sector uses, private data centers. So the takeaways are the cost savings of moving to the cloud enough to motivate utilities to take on the additional risk? And are the properties provided today sufficient to meet the requirements that they have? For us researchers, can we build trustworthy power applications efficiently, because cost is a huge factor? What security properties should be provided by the infrastructure versus can be composed outside? What's the trade-off? And how should regulations be changed to enable transition to the clouds? And the point is, regulations will change when there is enough confidence that these systems are working. Anyway, that concludes my talk. Thank you for your attention.
All right, questions? I have one. So I found this really interesting, and I think when you set up your talk, you sort of partition the set of problems into kind of real-time things. You said, let's not move these to the cloud, and I think that's definitely a very cautious and a prudent thing to do. But just putting prudence aside for a second, some people have talked about telemedicine or even telesurgery and things like this. So what would it take to actually put the kind of tight control loop of these systems into a networked environment? That, what would be the kind of biggest roadblocks to actually making that happen?
So I think it's a slight nuance. I think they're already networked right now, right? I mean, the question is who owns the infrastructure and who runs it? And that goes to Mike's point. Today it's run by your employees, or sometimes sometimes we lease lines. Power sector leases lines from communications companies, telecom companies. So in that sense, they're networked. It's already happening on the network. The question is, there is a feeling that they're in control of that network because either they have a contract or a lease on it versus they own the infrastructure versus now the infrastructure is owned and operated by somebody else. And this is a matter of bridging the trust, and from a non-technical perspective, and from a technical perspective is to say that can we do that by providing some technical guarantees which don't exist. I often hear that you can go to a cloud, an encrypted cloud, for example, but the cost is so high that the savings you get in moving to the cloud is nullified. So that's a factor as well. That answers your question. Yeah.
So my question is not so much about trustworthy, but about data computation. So one of the reasons why we move data to the cloud is cheap data intensive computing. For power operations, do you have a sense of how much data are being processed every day, how much computing?
Yeah. So power sector is quite wide. So I'm going to pick points and sort of give you a sense. So in the past, we collected data maybe once every few minutes. We got some information and sort of made sense of it to run the system. Now they're installing sensors that provide data at 30 or 60 samples a second. So that's increasing. Probably still not as much as what Google or the big data centers handle, but it's quite significant. I believe they can be up to 100 terabytes, maybe a day sometimes. Maybe I should get it. I don't know if it's a day or a year. I'll double check. So the point is the data is increasing. If you look at the generation side of stuff, it's actually quite different. So the generators, that like turbines that are running in the power plant, generate so much data every second already. But the question is they don't have to move it anywhere. It's in the same location, right? They can analyze it locally. And the turbines are actually so complex that power system operators don't run them. And they own them, they operate them, but the company that provided the turbine is constantly monitoring the turbine remotely as well and fine-tuning it. So the fine-tuning of the turbines is remotely done by the provider, whereas the power plant operator just sort of runs everything else. And so there is already places where this outsourcing is done, but it's done over models that are built over time and trust built over time.
Hey, so it looked like your primary focus was on moving existing applications into the cloud. Mm-hmm. Have you thought about how moving things to the cloud could actually allow the deployment of new applications? Because that might actually help spur the move. Because, right now the reason that all of us use the cloud for lots of things is because it lets us do things like, have your cell phone do stuff that we couldn't do before.
No, excellent point. So unfortunately I didn't get enough time to elaborate on it. It's true that you can actually open up a lot more. You can drive innovation by moving to clouds. Like I said, it's because of right now there's vendor lock-in to get a new application into the power system operators. Unless the vendor is providing it, he has no option. So, and also having all the data in one place for example, especially if it's a community cloud, I mean, it's excellent opportunity for running new kinds of applications. Unfortunately, though, it's like I don't know. So I have that as one of the drivers. But the question is, when a power utility is trying to make a decision, they're making a decision based on an individual business perspective. So the question is, are they going to invest money to move to cloud? Because in the long run, when everybody moves, there's going to be a benefit. It's always a challenge when these situations arise. It's like the problem of the commons. So,
don't you think this problem or this issue need to be solved in two steps? I'd say maybe it's too radical for these companies to start using a public cloud or a shared cloud. Because I have some experience talking to some people from these companies. What they are planning right now is mostly to try to build their own cloud, their private cloud, and virtualize a lot of resources that they have on the field. I don't know what you think about this.
I completely agree. And I think them shifting directly to a public cloud is not going to happen. So one of the things actually, I probably in a different version of these slides I had, what's the right model for them? Is it a community cloud, for example? And in essence, even if you look at the stuff that already moved to the cloud, consumer-facing stuff, it says software as a service. I guess it's probably what you want, but it's a solution as a service. And typically, like GE Grid IQ, the solution or software is so specific, nobody other than the power sector would use it. In essence, it's already a community cloud. So you're right, and that's why they already have data centers. I think they're getting familiar with this cloud technologies. They all use Hadoop, MapReduce, and stuff in the. And then the question is, should they move to a common? Probably the next step would be to a third-party cloud, in the sense that it's still not open, but they don't own the cloud, the data center, but they're sort of leasing the data center or third-party operated data centers. So it's going to be a gradual process. I'm trying to put it in front of the researchers because we have the luxury to look ahead maybe 15, 20 years or more, whereas the companies don't. Yeah. Thank you.